Okay, so let's continue our NumPy and Jupyter Notebook exploration. So I will just briefly review what we went through last time. So we have started exploring NumPy, which is a Python package for numerical arrays and their manipulation. So most of the data comes as arrays of sort of the same type variable. Okay? So we have arrays of integer numbers or arrays of floating, what we refer to as floating point or real numbers. And then we want to effectively manipulate them. So first thing first, I have to define an array, and this is an example of how I define a 2x2 matrix. And I think one of the most used 2x2 matrices that we're going to have in this course will be 1, 2, 3, 4. And both for in a 2x2 arrangement and 4x1 arrangement and so forth, because that's what we can come up with on the fly really easily. And then I can manipulate. So I can, for instance, multiply each element by the same number, and I operate on all of the array elements at the same time. One thing that we have to be careful with Python is when we refer to individual element and I want to grab it, they start from 0. So there's a little bit of a calculation that has to happen in your mind. So basically you have rows 0, 1, and 2, when matrix has total of 3 rows. Okay? So 3 is this ending point that you don't use, right? Row 3 in itself doesn't exist even though you have 3 rows. So when I want to grab an element, I'm going to say A of 0, 0 or 0, 1. First location is for row, second location is for the column. Okay? And I can grab multiple columns. I'm not going to review this in detail, but you can grab multiple number of rows and columns in their selection at the same time and basically isolate a subset of your array or your matrix. Okay? Excellent. Then I can do some standard linear algebra procedures of matrices. I can transpose a matrix. I imported NumPy as NP. I'm referring to NumPy as an NP. So every function that I used from NumPy, it starts from NP dot. Okay. So NP.transpose will transpose a matrix. It will do nothing to a 1D array. Okay. And then I can reshape as long as I have enough elements, I can reshape things around. So if I had a 2x2 matrix, I can reshape it into a 4x1 or 1x4. And be careful that when Python is populating this new matrix, it really just rearranges things in place. When it's populating it, it's grabbing things row-wise. So it goes through yours. Row 0 takes all of the elements and populate this new thing, and then goes to the row right after that. So row-wise. Python operates row-wise. Okay? As long as you have enough elements, you can change the shape and also find out what it is by using np.shape. Okay? And then, so this is this example of the row-wise. So if I had 1, 2, 3, 4, 5, 6 elements in a 3x2 matrix, I can change it to a 6, 1, and then I'm going to just grab elements. I just go down the row and populate this new shape, okay, with those elements. And in this particular case, it's going to be 6x1. Okay? And that's important to know, because you can scramble data really badly if you don't know that. You think you're doing one thing, but Python in the background is doing something else. Those are some of the most dangerous procedures. We can multiply matrices. The operation is called mat, or the function is called matmul, M-A-T-M-U-L, and it's also an NP function. And as long as I have matching dimensions, this is where dimensions are important, I can do the multiplication. Okay? And I can always basically do multiplication as long as I have correct number of elements. 1D arrays are not considered rows or columns, and I can always multiply a matrix and array as long as the number of columns in my matrix matches the number of elements in the array. 1D array. Okay? Okay. And then we opened up, really just opened up Jupyter Notebooks. So it's in your Anaconda Navigator. That's your set of distribution of packages that came also with Python. There's something called Jupyter Notebook. And I was kind of raving about it. And it's convenient in certain ways, you will see as we proceed. It's not convenient in some others. So just remember this. For larger projects, just like a larger project, it's always better to be in an environment like Spider. It's going to be easier to manage variables and so forth. And you will not have this additional, what I call software layer of sending things to your web browser, because when things go wrong, then that communication can break. Okay? So that said, it has like some really neat things for recording, and we will use it mostly for homework, though it is still your choice if you want to use Spider or some other. As long as you do your homework, we're good, okay? The particular choice of editor is not going to bother us too much. So if we open up Jupyter Notebook from Anaconda, I will exemplify, so I will just walk through a couple of slides to tell you what we're going to do. So there are different types of cells, or sort of code units. And some of them can be code, and some of them can be just text, which can make up nice reports. So that's one thing. And I will show you the example of this. And it's opened up in web browser. That way I can actually talk to remote computers really easily. And that's one of the great benefits of Notebook. And I can do some more advanced editing as necessary. And you have to note that when you have those cells and different formatting in Notebook, it's a different type of file. So whatever will be saved as IPYNB. NB stands for notebook, Python notebook. Okay. So, and regular Python file is .py. So because they're different files, there will be issues if you try to read one as another and the other way around. Okay? So it's file formatting, so file formats have to be correct before you do anything. They're not equivalent, but Jupyter Notebook environment can go back and forth between the two. So it can convert one to the other and go back. Okay? All right. So let's actually try them out a little, and we're going to have this exercise. Let me just open it back up. And you will have a little assignment. Let me just show you a couple of tests before we get that assignment going. So this is where I left off last time. I called my Jupyter, so you can open a new one if you don't have anything open. This is opened as new, but you can save something. You can say new notebook and open a new one if you'd like. You could save this one as, for instance, Python. You could export the Python code out of this. Okay. So there's sort of standard file editing menu right up here. You can make a copy. You can rename it. You can also rename just by clicking on it. Okay, I'm not going to do it because I tend to like this name. Okay, and it's going to do some auto saving, so it's not going to waste your work. But the best is if you actually go and do save as and save it where you know your files are. Otherwise, it's going to work in some default space. Okay, so let me show you. So this is a code cell, and this is simply assigning a variable a is equal to 3, and then np array. For that, I had to import NumPy as np. And this is where it's kind of really important to use print, otherwise the printing might not happen. So print command will force things to print. And if you notice, I kind of mentioned that at the beginning. I said sometimes you have to do print, sometimes it's just going to print it out anyway. This is this behavior where this additional software layer will not print things in a browser unless you specifically tell it to. Okay. So this just behaves just like any code, and it executes as you say shift enter or shift return. Okay? If something is hanging in this piece of code,
it's going to have a star here instead of a number. And that might be if you actually program something wrong and it cannot digest it. You can stop it by interrupting the kernel. So when you have to force things down, this is your first resort, is this stop here. just remember that. Your first resort to bail you out. Second one would be closing the browser or this particular tab. Okay. Now let me exemplify a markdown cell. This could be just text. This is a nice NumPy exercise. And it doesn't really do anything other than just put that text there, which is nice to have in coding. Okay. And I can still click on it and edit it. Okay, and it can be any type of text. And you can do any kind of formatting here you'd like. I'm not going to go and teach you how to format that. I could have done just here, do the regular coding thing. So by the way, by putting this symbol, you can put that text there, and anything after the symbol is ignored as far as code goes. It's just for your eyes, it's just for humans to read. So you can always have that. And if you're doing homework, which all of you have started, right? Right? The best thing is to have, and this is why we like this for homework, one cell per problem. So you're going to say problem, if you know how to type, 1B, say, I don't know what 1B was. And then you do that in one cell, and for the next problem, you do a different cell, and you say problem 2B, 1C, and keep going. That way, it's easier for you to locate where things are, and it's easier for you to, okay? But you could also do this as this markdown cell, problem 1B. But here, let me show you some nicer formatting, and for this you need to know a little bit of LaTeX. So if I write Q, or I can write a symbol, but for symbols I can use these dollar signs, and any kind of symbols will go in between, or formulas. And I can just say mu. Going to give me mu, Greek letter, which is normally a symbol. So there's a whole lot of symbols that can be, there's like a little command that will execute them. So I can do that, or I can do something more involved as a formula. I'm going to, again, do a markdown cell, and I'm going to write down Darcy's law. You know what Darcy's law is about? How much flux goes through a piece of rock? So my flux, linear flux, which is volumetric flux divided by the area of the piece of rock, is equal to minus, and there's a fraction going on, and that fraction has permeability K on top, and viscosity mu, which is why I introduced mu, on the bottom. And then what? What is my flux proportional to? What's driving the flow? To have flow of fluids, like regular flow of fluids, what do I have to have? Pressure difference, right? Without pressure difference, nothing's moving. Okay? And then flow goes from high pressure to low pressure. But pressure difference per length is gradient of pressure, and that's nabla P. Let's see what happens. Woohoo! I have a nice formula. So, editing nice formulas versus the code that actually executes them. Okay, let me go back there. Yeah. Okay. So this is a command for fraction. And in fraction, I have two things, numerator and denominator. And both of them are enclosed in these curvy brackets. So the one on top is k, the one on bottom is a symbol mu. And it's a symbol, so it's actually a command, /mu. And slash means, okay, it's a command. Don't take this as mu, take this as a symbol, right? And the numpy is another symbol like that, and p. Think you will need help with this? It has to be marked down cell. You should not have in here. So change your cell to markdown. You need to let it know it's not code, right? It's not that smart. And you can say, hey, you can have some regular text here. This is Darcy's law. And when I execute, again, Shift Enter, woohoo!
How do you go back?
Double click. And then you can also send this to a separate line to have like even better. So double dollar gives you a nice formula in a separate line. Double dollar for separate line. Huh? I will not teach about markdown cells. This is about coding, this course. But if you want to explore more your reports and you can combine whatever equations you might have with your code, which is powerful for reports. Okay? I will just say that these rules of how do I type in these formulas, the rules for typing formulas or typesetting is the correct formulas come from LaTeX. So if you need to Google, you Google LaTeX formula, and you will find these lists of how you refer to different symbols and so forth. You can typeset pretty much anything you possibly could imagine. You can go as fancy as you'd like. I'm going to stop teaching about Markdown right now, but it's for your use, for you impressing your future professors in different other courses. Again, the cell has to be a Markdown cell. It's not going to be treated as code. I want to make one more comment, and I'm not going to teach much more about it other than, okay, why couldn't I define an array just by putting brackets around numbers 1, 2, 3, 4 and calling that a Numpy array? Right? So we said, to say, I had to go through this entire procedure versus I could possibly, why not just this? It's called a list. And the problem is the following. This is actually, both are possible. Actually, this is possible too. Okay? However, this is a numerical array of strictly numerical values. This, I could technically just write in Masha here, and it'd be cool with that. It's a bunch of objects clustered together. In some languages, it's called a record. This particular here is called a list in Python. And again, anything after the symbol is ignored as the code. This is called a tuple. Going into details, what is the difference between list and tuple? I'm not going to go there. It's a little bit advanced. But the whole key is that I can bunch a whole different types together. Integers, real numbers, text, you name it. It can all go into that tuple or a list. List is something that I pass to a function. And again, I can have all kinds of objects in there. Okay? And that's why we need sort of a separate way to define an array of strictly identical numerical values. Okay? So I'm going to say this is array of strictly identical numerical values. It's just a bunch of different types clustered together. Okay. So all of these three definitions are possible. And in all of them, I'm going to say, hey, C of 0 is 1, D of 0 is 1, and E of 0 is 1, and I'm going to reference them the same way. So on surface, it appears like they're behaving the same way. Okay? But if you're engineers and you're dealing with a bunch of permeabilities in a matrix, please use NumPy arrays for speed. Okay? Then Python knows these are all the same objects and can flip them around much faster. And if you have 1 million of them, it matters. It really matters. Okay? So I'm just going to put use NumPy arrays for numerical arrays for speed. And being able to multiply matrices and whatnot. So those operations travel with NumPy arrays. Even though on the outside, it might appear that they all kind of behave similar. And Python will allow you to define them kind of in a natural way. Okay. Now let's go, just to see that you will be able to work on your homework. Let's do this little exercise. You should know everything from here, so it's just a recap. But try it out in JupyterNotebooks. So attempt to define a variable named aim-h and assign a value of 5 to it. Like a little minus h. Can you define that way? Why or why not? Because if you say a minus h equals to is assignment, right? 5. What happens? Why? Minus is an operator, so it's confused. It wants to do minus, but then it doesn't know what is a, what is h. You haven't defined them yet. Okay. And then why, if you have an a and h, well, why are you assigning anything? Right? So it gets thoroughly confused. So avoid special characters in your variable names. Okay. Now create two matrices A and B of size 3 by 3 and check whether A times B is B times A. And for these you have to know NumPy and
how does it do matrix multiplication. And if you have totally forgotten, I'm going to be kind and say, so NP array is the function you use to assign or to create matrices, and NP mat mul is the one for multiplication. And then shape. Or rather, to change the shape, you would say a shape equals to something.
So is A times B the same as B times A? Unless you really got lucky, and if it did, go play lottery or something.
Or maybe you defined very simple, if both of your matrices were diagonal, that means that they had elements only on diagonal and otherwise zeros, then it's going to be the case. But if you had a full 3 by 3 matrix,
so a whole bunch of operations like this, you will be basically redoing your homework 1 in Python. Do note that there are certain things because of the Python implementation that will act differently than what linear algebra says they should. So understand that there's theory and then there's implementation of it. One example is adding a scalar to an entire matrix. Python will do it. Linear algebra says, no, these two don't have the same dimensions, right? So that's something that you have to be attuned to. Okay. Can I move on? Everybody has gotten a chance to try this out. How about change of shape? That's fine? Okay. So now we will actually go a little move forward. So once you get into Dr. Volkov's reservoir simulation class, he will not be happy with 3 by 3 matrices, trust me. 3 by 3 by 3 does not describe any good reservoir. No numerical scheme converges on it either. So we need something larger. How do I define myself some larger arrays? Without typing them in, just create them in a certain range. Okay? So there are certain built-in functions that do that. And we will first exemplify 1D arrays using linspace, arrange, and log space. And all three are from NP, so every time I'm typing it in, I'm saying NP linspace, NP arrange, NP long space. Let's do this. So again, I want larger arrays, building larger arrays. I have already imported NumPy, so I'm good there. So let's say that we just say x is linspace 110, and then print x. Let's see what happens. And I'm also going to print x shape. So it seems that I got 10 numbers. Okay. They start at 1 and at 100. And the spacing between them is 11. Okay? So basically what it did is like starting from 1, ending at 100, give me 10 elements, equally spaced. So these are equally spaced linearly in between. You can change to 100 of them if you'd like. Then you'll get 100, 1, 2, 3, 4, 5, and so forth. So if I change to 100, I'll get this. You can play with that. You could go wild. But then there's trouble printing them all out. You could go a million. I'm not going to print that into my web browser. Okay? This is where you don't print anything. If you create a million of something, don't print it. Okay? Or it won't. It might lock up your web browser. This is where I say, like, use Spider maybe. Okay? Not. Excellent. So that's one of them. I could do the same thing, and this is really depends on, so copy the text here, okay? Learn how to use cut, copy, paste. That's called the reuse of code. And just say arrange. And I'm going to actually force it to do the same thing as above. So I'm going to say, give me spacing of 11. Okay? What are the differences here? Doesn't actually, so it doesn't include that endpoint, which is a little annoying. If I want to force it to include 100, I actually need to say, oh, this would work. Something larger than, then it's going to fit it. Because that 11 spacing was precisely on the dot, it cut off the last. If it's not precisely, it's still going to go include the 100. So this is that finicky parts of implementation for any programming. But this is essentially equivalent. So these two are equivalent. And arrange has that rule that it's going to not include an ending point, right? So this ending point is not included, but just a little less than, okay? But again, you can play with the spacing. So maybe spacing is important in whatever it is that you do. And that's what's defined. You want spacing of 2 between numbers. Or you want to precise, so you use linspace or range based on your preference, whatever the problem is calling for. Just be attuned to the small implementation differences, okay? And there's also log space. So I'm going to say, hey, np log space.
So I'm gonna work in powers of 10. So log of the first number is 1, log of the second number is 2, and log of, so this is if you were doing a log plot and you wanted equally spaced things in log space. Log space gives you equally spaced numbers on a log plot. When you take a log of it, they're equally spaced. Okay? Logarithm. Base 10. Again, that might be helpful in some applications. Yes?
Did you tell to start from 1?
Yes. 10 to the 1, right? 10 to the 1, 10 to the 2, 10 to the 3. That's 1 to 3, right?
So log of this is equally spaced between 1 and 3.
Yes? Okay. So those were for single arrays. These are all one-dimensional arrays. So we saw that the mention here, for instance, was 10 and nothing. So those were 1D arrays. Let's create some 2D arrays. So what happens if I say I? So I'm going to say 2D arrays. So I could say I, so this is identity. Remember identity matrix? What is identity? Ah, and then I do need to print it. Okay.
So identity of 4 will give me a 4 by 4.
Identity is useful, but it's more useful to create
A variety of numbers. They're kind of evenly distributed in a certain range. Here's an example. Let's say that you're in a reservoir and you measure in one portion of the reservoir, wherever your K zone is, you measure that the porosity is 20%. Now in reality, okay, you know that the porosity is on average in that block 20%, okay, or 0.2, but it's not 20% precisely everywhere. If you hit the reservoir like that, let me know. Okay, or you could play a lottery. So most of the time it's some sort of sequence of numbers, probably between 10 and 30. Okay.
So to get a random distribution of numbers in general, there is a rand function. Okay. So I'm going to now create a matrix. I'm going to call it R. And there's NP random, and that random has a sub function called rand.
So just if you think about NumPy or NP as last name, well, some people have two last names, eh? So this is sort of a subfolder of functions in NumPy.
Is random, and then there is rand. And if I just say 4 by 3 this time, just for kicks, let's print R and see what happens.
So these are random numbers that are actually between 0 and 1 by default. Now I can scale them however I'd like. Okay. So how would I make all of these numbers from 0.1 to 0.3? I want my porosities to be in the range 0.1 to 0.3.
So I'm going to say R1 is, how am I going to scale this?
I can multiply, I can shift values.
What will happen if I say 0.1 plus R?
It's going to be a shift, but instead of 0, they will all start from 0.1. So that's part of what I want. But they will go to 1.1. Yeah? So I got to shrink the range. How am I going to shrink?
multiply by? I want it to go up to 0.3 ultimately. And these r's, they go from 0 to 1. I want them to end at 0.3. Keep going. Yes? Scaling. So then all of these will be from 0 to 0.2 and shift them by 0.1. Yes? I'm going to put a comment to shift 0, 1 range to, in general, A, B range multiply by B minus A and add A. Make sense? Then they will all start from A and have the difference between B and A. Yes. This is, of course, assuming that B is larger than A. But it would work in negative as well. Excellent. So this is now, this would give me the following, rather. Would give me porosities in 0.1 to 0.3. Sort of on average 0.2. So that's very useful when we have one measurement, but we really need a distribution of realistic values close to that measurement. More about this in geostatistics and reservoir simulation. Okay? Okay? And a couple of more simple things. Oh, and I forgot, of course, to print my R1. There we go. Visual test. Is there anybody smaller than 0.1 or larger than 0.3? I don't see. Okay. And a couple of more useful commands. So I'm going to say A is, I could get, or D maybe. D is a diagonal matrix. Diagonal matrix has values only on diagonal, so whatever values you want on diagonal. Of course, I'm not going to steer away from my 1, 2, 3, 4. Why? And then I do need to print it. And I will get 1, 2, 3, 4 on diagonal. And the rest is zeros. And then this is letter O is NP zeros. And you just give it a size. I'm going to stick with 4. If I want a matrix here, I should add full dimensions, but it could be zeros of any dimension. Oops. Ah, it wants this. And we can do, well, let's have both examples. So note when you kind of do print after print, it's just going to pack everything together. So there's two things here, yes? You can, you're going to get to printing, but you can print a little break here. Okay? Or a space or something. Otherwise, it just piles them up, and sometimes it's a little hard to see. And then one final that is kind of useful, I'm going to call this one K, is NP1s. And of course I have to print it. And by default, it's going to give me a 1D array. Otherwise, I would have to have 4 by 4 matrix. Okay? All right. So now you're equipped to actually kind of create very large matrices as you need them to. And some effective arrays. Okay, if you want to plot functions, I don't want to type in all of the values. To plot a sine function, I'd like a range of values from 0 to 2 pi and then plot it. Right? So we're going to work with those. Again, no matter how large is your array, you can call functions on it and do arithmetic with it. So there is, for instance, np sine function is np.sin. I can do it on the entire array no matter how large the array is, which is very valuable. So we're going to do that next time and start plotting them to actually see our results as well. So plotting exercise is next.